There is a fact about space travel that sounds like a mistake the first time you hear it. The closest planet to the Sun, Mercury, the innermost world on every diagram you have ever seen, is one of the single hardest places in the solar system to actually visit. One spacecraft flew past it in 6 months. The one that wanted to stop and orbit needed 6.5 years. Same planet. The only difference was the act of stopping. And that difference, it turns out, is the secret that governs everything out here. The reason a trip to Mars costs the better part of a year, and a trip to the edge costs the better part of a decade. We are going to travel this whole solar system tonight, world by world, and learn why the times are what they are. Settle in. Subscribe if you haven't yet, because by the end of this, the word distance will mean something completely different to you than it does right now. Let's slowly slip into this. Part 1. The question you already answered wrong. Almost everyone, the first time they really sit with this question, does a little piece of math without noticing they are doing it. You think of the moon. You know, in some loose way, that the moon is about 384,000 kilometers from where you are sitting right now. And you know that the astronauts who went there did it in roughly 3 days. So your mind takes that single fact and quietly stretches it across the whole sky. If the moon is 3 days away, then surely Mars, the next obvious stop, is a week, maybe 2 weeks if we are being careful. The outer planets feel like they should be a long summer's drive, the kind of trip you would complain about but survive. That is the instinct. It is gentle, it is reasonable, and it is almost completely wrong. Here is what that quiet little calculation leaves out. When Mars comes as close to Earth as it ever gets, swinging to the same side of the Sun as us at just the right moment in both of our orbits, it sits about 56 million kilometers away. Hold that number against the Moon for a second. 56 million kilometers is roughly 146 times the distance to the Moon. So if the Moon took 3 days, then the very nearest approach of the easiest planet, on its best possible day, is already something closer to a year and a half of moon trips stacked end to end. And that is the easy one. That is the gift. By the time we walk outward to the giant planets, you stop measuring the journey in days or weeks or even months. You start measuring it in years. And out past those, you start measuring it in decades, in spans of time long enough that the person who waved goodbye at the launch is not the same person who would be alive to see the arrival. It is worth dwelling on just how badly the intuition fails, because the size of the error is itself a kind of lesson. The mistake is not that you are off by a little. The mistake is that you are off by factors so large they stop meaning anything. The moon is the only other world human beings have ever physically stood upon, and it is, in the scale of the solar system, practically in our laps. If you shrank the Earth down to the size of a basketball, the moon would be a tennis ball about 7.5 meters away, close enough to see clearly across a room. On that same shrunken scale, Mars at its nearest would be more than a kilometer away, and the outer planets would be tens of kilometers off. And the little spacecraft we sent to Pluto would have to travel something like the width of a continent. The moon is the doorstep. Everything else is another country, and some of it is another country on the far side of an ocean. And the carousel image is worth holding precisely because it captures the part our instinct refuses to model. When you imagine driving to a town, the town has the decency to stay still. But every planet is racing around the sun at a speed that would be difficult to even picture. The Earth beneath you is carrying you around the sun at roughly 30 kilometers every second, which is about 107,000 kilometers per hour, faster than any bullet, and you feel none of it. Mars is doing the same thing at its own pace, and Jupiter at its own slower pace, each on its own track, each at its own speed, none of them waiting for you. To travel between them is to leap from one spinning platform to another, across a gap that is itself changing every second, aiming not at a place, but at a future. That is the machine, and learning to think the way it moves is the whole secret of everything that follows. We are going to travel through this entire solar system together tonight, slowly, one world at a time, in the order the planets actually sit as you move away from the sun. And by the time we reach the far edge, you will know the real travel times. You will know that it took one spacecraft 6.5 years to reach the planet closest to the sun, and another spacecraft 9.5 years to reach the world at the frozen rim. But the numbers are not really the point. The numbers are easy to look up. What I want you to walk away with is something stranger and more useful than a list. I want you to understand why those times are what they are. Because once you understand the why, the entire night sky reorganizes itself in front of you, and it never looks the same again. The first thing you have to let go of is the picture in your head. Most of us carry a diagram of the solar system that we absorbed as children, and in that diagram the planets are little fixed dots sitting politely on their rings, waiting. In that picture, traveling to a planet is like driving to a town. You point the car at the town, you press the pedal, the town stays where it is, and eventually you arrive. That picture is comforting, and it is a lie. The solar system is not a set of fixed targets. It is a machine. Everything in it is moving, all the time, at tremendous speed, along curved paths, and the moment you accept that, you realize that getting anywhere in it is less like driving to a town and more like trying to hand something to a person on a spinning carousel while you yourself are standing on a different, faster carousel. You cannot just reach toward where they are. You have to think the way the machine thinks. So that is where we begin, not with a rocket, but with the rules of the machine. Because the distances are only half the story, and they are honestly the less interesting half. The real story is in the motion, in the timing, and in a single brutal fact about space travel that almost nobody thinks about until it stops them cold. There is a reason the closest planet to the Sun is one of the hardest places in the solar system to actually visit, and that reason is going to overturn the first assumption you ever made about all of this. But before we can get to Mercury, before we can get anywhere, you and I need to learn to think like the machine. We need to understand why pointing a rocket straight at a planet is almost always the wrong thing to do. Part 2. Learning to think like the machine. The planets do not travel in circles. This is the quiet fact that breaks every simple version of this question. We draw them as circles because circles are easy to draw, but the real paths are ellipses, gently stretched ovals, and that single geometric truth has an enormous consequence. It means there is no such thing as the distance to Mars. There is only a range. Sometimes Earth and Mars sit on the same side of the Sun, lined up neatly, and the gap between us shrinks to that 56 million kilometre best case. And sometimes Mars is all the way around on the far side of the Sun, hiding behind it, and the gap stretches out to about 400 million kilometres. Same two planets, same orbits. The distance between them is constantly breathing in and out as both worlds run their laps at different speeds. When you ask how far away Mars is, the only honest answer is another question. You have to ask, far away when? This is why timing is everything, and why the moment you choose to launch matters as much as the rocket you launch with. We call that moment a launch window, and it is not a marketing phrase. It is a hard gate written into the orbits themselves. If you miss the alignment, you do not simply leave a little late. You wait, sometimes for years, until the two worlds swing back into a workable arrangement. The machine opens a door, holds it open for a little while, and then closes it, and there is nothing you can do to argue with it. Now here is the part that genuinely surprises people. Because the target is moving, pointing your spacecraft directly at the planet is almost always exactly the wrong thing to do. If you aim at where Mars is on the day you launch, then by the time your spacecraft crosses that enormous gap, Mars will have moved on, far ahead along its own orbit, and you will arrive at an empty patch of space where the planet used to be. The correct technique has a name. It is called a Hohmann transfer, and it is the foundation of nearly every interplanetary trip we have ever flown. Picture a path shaped like half of an ellipse, a long, graceful curve that begins at Earth's orbit, swings out and around the Sun, and meets the orbit of the target planet at exactly the right moment so that the spacecraft and the planet arrive at the same point in space at the same instant. You are not aiming at the planet. You are aiming at a rendezvous. There is a comparison that makes this click, and you have probably seen it 1,000 times without thinking of it this way. Imagine throwing a pass to a runner in a game. You do not throw the ball at where the runner is standing, because by the time the ball arrives, the runner will have sprinted past it. You throw the ball to where the runner is going to be. You lead them. Every successful mission to another planet is, in essence, an enormous, patient pass thrown across hundreds of millions of kilometers to a receiver who will not arrive at the catch point for 7, 8, 9 months. The Hohmann transfer is the most fuel-efficient route we know how to fly. It asks for the least propellant, and the price it charges in exchange for that efficiency is time. The cheapest path is almost always the slowest one. It helps to understand why the ellipse is the cheap path, and not just a quirk of geometry. When your spacecraft leaves Earth, it is already moving at Earth's tremendous orbital speed around the Sun. To reach a planet farther out, you do not need to point yourself outward and fight your way there. You simply need to add a little speed in the direction you are already traveling, which lifts the far end of your orbit until it just brushes the orbit of your target. You then coast, engines off, falling around the Sun along that long curve, trading the energy you spent at the start for the height you gain at the end. It is less like driving and more like throwing a stone uphill and letting it arc. The whole transfer is mostly coasting, mostly waiting, mostly silence. The engine fires hard for a few minutes at the beginning, and then for most of a year there is nothing to do but fall in exactly the right direction and trust that the arithmetic was correct. This is also why the launch window cannot be argued with. The planets only line up for one of these cheap transfers at regular intervals, and the gap between those chances depends on how the two orbits beat against each other. For Earth and Mars, a good launch window opens only about once every 26 months. Miss it, and you do not wait a few days for the next flight. You wait more than 2 years for the geometry to come back around. The machine runs on its own schedule, indifferent to ours, and the people who fly these missions spend years of their lives racing toward a door that the solar system will hold open for only a few weeks. There is one more tool in the machine, and it is the closest thing space travel has to a free lunch. It is called a gravity assist, and the first time you understand it, it sounds like cheating. When a spacecraft swings in close to a planet, it can borrow a small fraction of that planet's own orbital motion. The planet is moving around the Sun with staggering momentum, and a passing spacecraft can steal a sip of that momentum and come away faster than it arrived, flung onward toward its next target without burning a single extra gram of fuel. The planet pays for it, in theory, by slowing down by an amount so unimaginably tiny it could never be measured. The spacecraft gets a velocity boost for free. This is not a minor trick. The spacecraft called Voyager 2 used 4 of these gravity assists, chained together, one planet handing it off to the next like a relay, and without that sequence, a mission to Neptune flown with the kind of propulsion we actually have would need more fuel than any rocket ever built could lift off the ground. The free lunch is sometimes the only lunch on the menu. The way a gravity assist actually works is worth understanding, because it sounds at first like getting something for nothing, and it is not quite that. When a spacecraft falls toward a moving planet, the planet's gravity pulls it in, swings it around, and lets it go again. If the planet were standing still, The spacecraft would leave with exactly the same speed it arrived with, gaining nothing. But the planet is not standing still. It is racing around the Sun, and as the spacecraft swings past, it effectively grabs onto that motion and is flung forward in the planet's direction of travel, like a small stone caught in the wake of a passing truck and dragged along. The spacecraft speeds up relative to the Sun. The planet, in exchange, is slowed by an amount so unimaginably small, given the staggering difference in their masses, that it could never be measured. It is a real transaction. The planet pays. It just pays so little that the cost rounds to nothing, while the spacecraft's gain can be enormous. The spacecraft Voyager 2 is the masterpiece of this technique, and its journey shows what the relay makes possible. Launched in 1977, it did not carry anywhere near enough fuel to reach the outer planets on its own engines. Instead, it used Jupiter's gravity to fling it onto Saturn, then Saturn's gravity to fling it onto Uranus, then Uranus's gravity to fling it onto Neptune, 4 planets handing it forward, one to the next, like runners passing a baton, each adding speed for free. Without that chain, a mission to Neptune flown with the propulsion we actually have would require more fuel than any rocket ever built could lift off the ground. The free lunch, in this case, was the only thing that made the meal possible at all. And it only worked because the planets happened to be lined up just right. A lucky arrangement we will return to when we reach the worlds at the far end of that relay. So that is the frame. That is the machine. Ellipses, which mean there is no fixed distance, only a range. Timing, which means the launch window is a door that opens and closes. And borrowed gravity, the relay of free momentum that makes the impossible trips merely very long ones. Keep all 3 of those in your mind as we begin to actually move outward, because they explain everything that follows. And the very first planet we come to, the one closest to the Sun, the one your instinct says should therefore be the easiest to reach, is about to take all 3 of those rules and use them to teach you that in space, closer does not mean faster, not even a little. Part 3. Mercury and the lie of closeness. Mercury is the first place the machine makes a fool of your intuition. It is the closest planet to the Sun, the innermost world, the one that on every diagram sits nearest the center. And it is one of the single hardest places in the entire solar system to actually stop at. That sentence should feel wrong to you. It felt wrong to the engineers too, until they did the math, and the math is merciless. To understand it, you have to stop thinking about distance and start thinking about energy, because the trip to Mercury is not a problem of how far. It is a problem of how fast and in which direction. Here is the trap. The Sun is the most massive object in the solar system by an overwhelming margin, and its gravity defines a kind of valley, a slope that everything in the solar system is perched upon. Earth sits part way up that slope. Mercury sits far down near the bottom of it, close to the Sun, deep in the gravitational valley. And when you send a spacecraft from Earth inward toward Mercury, you are not climbing toward it. You are falling toward it. The Sun's gravity grabs your spacecraft and accelerates it, faster and faster, the whole way down. By the time your spacecraft reaches the neighborhood of Mercury, it is moving at a tremendous speed, far too fast to simply slip into orbit. If you do nothing, you do not arrive at Mercury. You scream past it and fall onward toward the Sun, and Mercury is left behind in the rear view, a missed exit on a highway with no way to turn around. This is where we meet the single most important and least appreciated fact in all of space travel, and we are going to return to it again and again until the end of tonight, because it secretly governs everything. In space, stopping costs exactly as much as going. Slowing down is not free. There is no air to push against, no brakes to press, no friction to bleed off your speed. The only way to lose velocity is to fire an engine in the opposite direction. And firing an engine means burning propellant, the same propellant, in the same quantities that it took to build up that speed in the first place. To arrive at Mercury and actually stay, to shed all that velocity the sun's gravity poured into you on the way down, you have to carry and burn an enormous amount of fuel doing nothing but braking. Closeness, it turns out, is a trap. The planet that is easiest to fall toward is one of the hardest to stop at. There is a way to feel this in your body, even though it happens in the silence of space. Think of the sun's gravity as an enormous hill, with the sun at the very bottom and the planets resting at different heights on its slope. Earth sits comfortably partway up. To go outward to Mars or Jupiter, you are climbing the hill, which is hard work, but which the universe lets you do slowly, coasting most of the way. But to go to Mercury, you are doing the opposite. You are rolling downhill toward the sun, and the hill does to you exactly what hills do. It speeds you up, faster and faster, whether you want it to or not. By the time you reach the bottom where Mercury waits, you are moving so fast that simply stopping there is like trying to catch a ball that has been dropped from the top of a skyscraper. The energy you must shed is enormous, and every bit of it must be paid for in fuel you carried all the way down. Mercury is at the bottom of the deepest part of the hill we ever try to reach, and the trip down is the trip that punishes you most for arriving. The mission record tells this story with almost cruel precision. The first spacecraft to reach Mercury was called Mariner 10, and it arrived back in 1973 using a gravity assist past Venus to help it along. It got to Mercury in about 6 months, which sounds wonderfully fast, and it was. But Mariner 10 could not stop. It was never going to stop. It went hurtling past Mercury, snapped its photographs in the brief minutes it had, and continued on, looping around the sun and coming back for a few more fleeting passes, but never once slowing enough to settle into orbit. It was a series of waves through a train window, not a visit. The first spacecraft that actually managed to orbit Mercury was called Messenger, and the difference in what it had to do is the entire lesson of this planet. Messenger launched in 2004, and to bleed off enough speed to let Mercury's gravity capture it, it had to fly a route of almost unbelievable patience. It looped past Earth once, past Venus twice, and past Mercury itself 3 separate times before finally, gently, on the right pass, allowing itself to be caught. The whole choreography took 6.5 years. 6.5 years to reach a planet that Mariner 10 had flown past in 6 months, and the only difference between them, the entire difference, was that one of them needed to stop and the other did not. That is how expensive stopping is. It is the difference between half a year and most of a decade, and the lesson did not end there. The most recent mission to Mercury is a joint European and Japanese spacecraft called Bepi Colombo, which launched in 2018. It is running an even more elaborate dance than Messenger did, a long series of flybys past Earth, past Venus, past Mercury, again and again, each one carefully shaving away speed. Originally, it was meant to settle into orbit around Mercury at the end of 2025, but space does not care about our schedules. In 2024, engineers discovered that the spacecraft's electric thrusters were not delivering full power, and the careful trajectory had to be recalculated around the shortfall. The new arrival, the moment it will finally slip into orbit around the planet closest to the Sun, is now the 21st of November, 2026, with its real science work beginning in the spring of 2027, years again. Years to reach the nearest planet there is. Before we leave Mercury, it is worth understanding why anyone would go to all that trouble for it, because the difficulty only makes the prize stranger. Mercury is a small world, but it hides an outsized secret in its core. The metallic heart of Mercury takes up an enormous fraction of the planet, something like 85% of its radius, compared with roughly 55% for Earth. It is, in a sense, a great ball of iron with a thin skin of rock pulled over it, and nobody is entirely sure why. And that iron core does something it has no business doing. It generates a magnetic field. A world this small, this old, should have cooled and stiffened inside long ago, its core gone solid and still, its magnetism dead. Yet Mercury still has a living magnetic field, faint but real. And that single fact is a clue to how the insides of rocky planets, including our own, churn and evolve over billions of years. There is more that makes Mercury a kind of archive. Its surface is saturated with craters, scarred again and again over the ages, and crucially, it has stayed that way. Earth erases its own history constantly, its surface recycled by drifting continents and weather and water, so that almost nothing of the violent early days survives. Mercury kept everything. Its face is essentially unchanged since the chaotic first chapter of the solar system roughly 4 billion years ago, a frozen record of a time our own planet long ago paved over. And in the permanently shadowed floors of craters near its poles, where sunlight never reaches even on the planet closest to the sun, there is water ice, sitting in pockets of perpetual cold, a stone's throw from the most blistering daylight in the solar system. Mercury is a planet that kept the receipts the rest of the solar system threw away, which is exactly why it is worth 6.5 years of someone's patience to read them. So let this be the first thing the machine teaches you, and hold on to it, because it is going to come back. The solar system does not grade on proximity. The map on your wall, with its tidy little rings, tells you Mercury is close, and in raw distance it is. But the machine measures everything in energy and speed, and the brutal arithmetic of slowing down, and by that measure, the nearest planet is one of the most distant places we know how to visit. Now we move outward, just one step, to a world that turns this lesson on its head in the opposite direction. A world we can reach in a matter of months, easily, again and again. A world that is, in every way that matters, completely impossible to stay on. Part 4. Venus, the world you can reach but never touch. Venus is the brightest thing in our night sky after the moon, and that brightness is the first of its deceptions. You have almost certainly seen it without knowing it, that single steady point of brilliant white that hangs near the horizon after sunset or before dawn, so bright that people mistake it for an aircraft, or a star behaving strangely, or something stranger still. That light is sunlight bouncing off the top of an unbroken deck of cloud, and the cruel joke of Venus is that its beauty, that lovely silver shine, tells you absolutely nothing true about what waits underneath. It is a gorgeous lid on a furnace. Venus matters to us, scientifically, for a reason that is genuinely unsettling. Venus and Earth are sisters. They formed at nearly the same time, from nearly the same raw material, in nearly the same region of the young solar system. They are almost the same size, almost the same mass, made of almost the same stuff. By every reasonable expectation, they should have grown up to be similar worlds, and instead they ended at opposite extremes. Earth became temperate, blue, wrapped in liquid oceans, crowded with life. Venus became the closest thing to a vision of ruin that the solar system contains. The surface temperature on Venus is about 465 degrees Celsius. Let that number settle. It is hotter than Mercury, even though Venus sits much farther from the Sun, because the heat is not really coming from the Sun anymore. It is trapped. The air itself presses down on that surface at about 92 times the pressure you feel at sea level on Earth, a crushing weight equivalent to being nearly a kilometre underwater. And the clouds, those bright, lovely clouds, are not made of water. They are made of sulfuric acid. The word sister is not poetry here. It is the precise scientific fact that makes Venus so unsettling to look at. Venus is about 95% the diameter of Earth, with about 80% of Earth's mass. It formed in the same era from the same swirling material, only a little closer to the Sun. If you had stood at the dawn of the solar system and looked at the two infant worlds, you would have had no obvious reason to predict that one would become a garden and the other a crematorium. And yet here they are. The difference between them is not a difference of raw ingredients. It is a difference of fate, of some chain of events that tipped one world one way and the other world the other, and we still do not fully understand what that chain was. That is the quiet menace of Venus. It is a demonstration that worlds which begin almost identically can end almost infinitely apart. The leading explanation for how a sister world becomes a furnace is a runaway greenhouse effect, a process that may have begun after Venus lost whatever oceans it once had. Once the water was gone, there was nothing left to absorb and lock away the carbon, and the heat fed on itself, climbing and climbing past any point of return. And here is why that is not just a curiosity. Venus is the nearest thing we have to a controlled experiment showing what happens to a rocky world when its climate crosses a line and cannot come back. It is a planet that ran the experiment for us, and the result is written on its surface in 465 degrees of heat. Understanding exactly when and why Venus tipped over is not an academic puzzle. It is a question with a mirror in it. Now, getting to Venus is, in raw travel terms, one of the easier trips in the inner solar system, and the mission record is full of relatively quick crossings. The first successful flyby of another planet in all of human history was a spacecraft called Mariner 2, which reached Venus in 1962 after a journey of 110 days, a little over 3 months. Years later, a spacecraft called Pioneer Venus made the trip in 1978 on a slower, more fuel-sparing path, and it took about 198 days, closer to 6.5 months. The European spacecraft Venus Express made the crossing in 2005 in about 153 days. Look at that spread for a moment. 110 days at the fast end, nearly 200 at the slow end, to the very same planet. That spread is not random. It is once again entirely about how much speed you are willing to shed when you arrive. A fast approach means you arrive carrying a lot of velocity, which means you must carry a lot of braking fuel. A slow, patient approach lets you arrive gently, carrying less fuel, but it costs you months. Every mission makes that trade differently, depending on what it is carrying and what it intends to do. The same lesson from Mercury in a softer voice. Speed is something you pay for twice, once to gain it and once to lose it. But reaching Venus and surviving Venus are two entirely different problems, and the gap between them is where the real horror of this planet lives. The only spacecraft that have ever sent back photographs from the actual surface of Venus were a series of Soviet landers called Venera. They are among the bravest machines ever built, because to land on Venus is to volunteer for a death that is only a question of how many minutes you can buy. Imagine being one of them. You are a sphere of metal descending through that bright cloud deck, and as you fall, the world outside begins to crush and cook you at the same time. The pressure climbs and climbs and climbs until it is pressing on your hull with the force of an ocean. The temperature outside passes the melting point of lead. Your camera shutter opens, and for a few moments you see it, the actual ground of Venus, a flat plain of cracked orange rock under a heavy orange sky, a place no human eye had ever witnessed. The image begins crossing more than 100 million kilometers of space back toward the planet that built you. And the heat keeps coming. Your electronics begin to fail in the oven. Your structure begins to give under the weight. The most durable of these landers held on, transmitting, for 127 minutes, 2 hours and 7 minutes. And then the signal stopped, and Venus closed over it. It is worth lingering inside those minutes, because they contain something close to heroism, even if the hero is only a machine. Everything about that descent was a countdown that the lander could not stop. The engineers who built it knew, before it ever left Earth, that they were building something to die. They were not designing for survival. They were designing for how many minutes of life they could buy before the planet won. And every system, every choice, every gram of insulation was spent on stretching that handful of minutes a little longer. The image it sent, that flat plane of broken orange rock under a heavy sky, is one of the rarest photographs in human history, and it cost the entire life of the thing that took it. We have many thousands of pictures of Mars. We have a small handful from the surface of Venus, and behind each one is a machine that lasted, at most, a little over 2 hours. That record, 127 minutes, has stood since the 1980s. We have not broken it. We have not, in fact, even tried again. The combination of heat and pressure and chemical corrosion made anything longer simply impossible with the engineering of that era, and the engineering of that era is, astonishingly, still the high water mark. So here is the strange shape of Venus, the second world out. It is a place we can reach in 3 or 4 months, easily, a place we have flown to many times, a place that shines down on you tonight, like a promise. And it is a place where the best machine we ever sent lasted just over 2 hours before the planet killed it. Reaching a world and staying on it are different questions with different answers, and Venus is the sharpest proof of that we have. Now we step outward once more, to the one planet where the question stops being purely scientific and starts, very cautiously, to sound like a plan. Part 5. Mars, where the numbers become personal. Mars is different from every world we have talked about so far, and the difference is not really about the planet, it is about us. Mars is the one place in the solar system where the phrase human mission shows up not only in dreamy speculation, but in actual government budget documents and serious engineering timelines. It is the world we talk about going to, ourselves, in person, and that changes the entire character of the question. For Mercury and Venus, travel time was an abstraction, a number attached to a robot. For Mars, the travel time is a number attached to a human body, with everything that implies. The reasons we are drawn to Mars are real, and they are old. Mars has a day that is startlingly close to our own. 24 hours and 37 minutes. A rhythm a human being could almost slip into without noticing. It has polar caps of frozen water. It carries, written across its surface, the ghosts of ancient rivers, the dry beds of vanished lakes, and the outline of what may once have been an ocean across its northern lowlands. It has a thin atmosphere, only about 1% of the pressure we breathe, made mostly of carbon dioxide, thin enough to be nearly useless to us, and yet thick enough to make landing genuinely difficult. And it holds the single most tantalizing possibility in nearby space. If life ever arose anywhere beyond Earth, Mars is the most probable place where some trace of it might still be found. That belief has steered billions of dollars and the better part of a century of missions ever since the 1960s toward this one rust-colored world. The distance to Mars, as we said at the very beginning, is not a single number but a breathing range. At the closest approach, in 2003, Mars came within 55.76 million kilometers of Earth, the nearest it had been in nearly 60,000 years. At its farthest, on the opposite side of the Sun, that gap opens to around 400 million kilometers. On average, the separation is about 225 million kilometers, and that average distance is worth translating into a different unit, because it tells you something a kilometer count cannot. At that average distance, the light itself, the fastest thing there is, takes about 12.5 minutes to cross the gap one way. That means, when we send a command to a rover on Mars, it travels for 12.5 minutes before it arrives, and any reply travels 12.5 minutes back. A simple yes or no question, asked and answered, takes 25 minutes. There is no conversation with Mars. There is only sending and waiting and learning to be patient with the speed of light itself. Using a standard Hohmann transfer and the chemical propulsion we actually fly today, the crossing to Mars runs about 7 to 9 months. The Mars Reconnaissance Orbiter, which launched in 2005, made it in just under 7 months. The spacecraft that carried the Curiosity rover took about 8.5 months, so the robotic trip is a matter of 2/3 of a year, give or take. But a human trip is a far larger thing, because a human cannot simply arrive and turn around. Once people are on Mars, they have to wait for the planets to swing back into alignment before the return journey is even possible, and that wait is long. A realistic crewed mission looks like 7 to 9 months out, then a surface stay of something like 14 to 18 months, while the launch window slowly reopens, then another 7 to 9 months home. From the moment you leave Earth to the moment you return, you are looking at something close to 2.5 to 3 years of your life. The shape of that mission deserves a closer look, because the long surface stay is not a choice, but a sentence handed down by the same orbital mechanics that govern everything else. You cannot simply land on Mars, plant a flag, and turn around. By the time your crew arrives, Earth and Mars have moved on in their orbits, and the cheap return window, the alignment that lets you fly home without an impossible amount of fuel, will not reopen for well over a year, so the crew must wait. They must live on the surface of Mars for something like 14 to 18 months, not because there is that much to do, but because the planets themselves will not permit an earlier departure. The mission length is dictated not by human will, but by celestial geometry. You go when the door opens, you stay until it opens again, and the door keeps its own schedule. That waiting is its own kind of trial. Picture spending more than a year on a cold, dry, irradiated world, in a habitat you cannot leave without a suit, knowing that home is a pale blue point in the sky, and that even a radio message to a loved one will take many minutes to arrive and many more to be answered. There is no quick return if something goes wrong. There is no rescue that could arrive in time. The crew that goes to Mars will be more alone and more committed than any human beings in history, bound to the surface by the same machine that brought them there. And here, the travel time stops being a logistics problem and becomes a biological one. Beyond the protective magnetic field of Earth, out in open space, the human body is exposed to a constant sleet of cosmic radiation, high-energy particles that pass through flesh and damage it on the way. The Curiosity spacecraft carried an instrument that measured this dose on the way to Mars, and the result is sobering. The journey alone, just the transit out and back, delivers a radiation dose of roughly 0.66 sieverts. A full emission, with a long stay on the surface, pushes the total toward 1 full sievert. To give that meaning, every sievert of exposure is associated with something like a 5% increase in your lifetime risk of a fatal cancer. And the historical career limit that the American Space Agency set for an astronaut across an entire working life sits down around 0.6 sieverts. Read those two numbers against each other slowly. The round trip to Mars, the transit alone, spends nearly an entire career's worth of allowed radiation in a single voyage. On top of that, the long months without real gravity quietly drain the density from astronauts' bones and weaken the muscle of the heart itself. It is worth slowing down on that radiation number, because it is easy to say and hard to feel. We are not talking about a vague background hum of risk. We are talking about a steady, invisible sleet of particles moving at nearly the speed of light, born in the sun's outbursts and in the deaths of distant stars, particles that on Earth are turned aside by our planet's magnetic field and absorbed by the thick blanket of our atmosphere long before they reach the ground. You have lived your entire life inside that shelter without ever once thinking about it. The crew, on the way to Mars, would step outside it for the first time in the history of our species and stay outside it for years, with nothing between their bodies and that sleet but the thin walls of a spacecraft. Every day of the journey, those particles would pass through them, tearing tiny tracks of damage through living tissue, and there would be no way to feel it happening and no way to make it stop. The barrier between us and the nearest reachable world is not really the distance at all. It is the simple, sobering fragility of the human body once you take away the shield it was born under. The microgravity is its own slow erosion. In the absence of any real weight to push against, the human skeleton begins to dissolve the bone it no longer thinks it needs, leaching away calcium month after month, and the heart, no longer working against gravity to pump blood upward, begins to weaken and reshape itself. Astronauts who have spent long stretches in orbit return to Earth, needing to learn, in a sense, how to be heavy again. A crew arriving at Mars after 8 or 9 months of weightlessness would have to do the hardest physical work of their lives, on a strange world, in bodies that the journey had quietly been taking apart. These are not reasons it is impossible. They are described, by the people who study them, as solvable engineering problems. But the crucial word in that phrase is the one we skip over. They are solvable. They have not been solved. And the thing that would solve the largest of them is not a better spacesuit or a cleverer habitat. It is a shorter trip. If you could cross to Mars in 3 or 4 months instead of 9, the radiation dose falls, the bones hold, the whole risk shrinks. What shortens the trip is more thrust, a more powerful kind of engine, and that is a thread we are going to pick up in full near the end of tonight, because it is the hinge on which all of this turns. For now, hold this image. Mars is the very edge of the places we can seriously imagine sending people in the near future, and even Mars, the easy one, the friendly one, the one with the Earth-like day, asks for nearly 3 years and a dangerous dose of radiation. And once we step past Mars, the entire scale of the question changes, not gradually, but all at once. The next world out is so large and so far and so violently hostile that it forces us to think about distance in a completely different way. Part 6. Jupiter, where years replace months. Jupiter is where the scale of this journey changes character. Up to now, we have been measuring trips in months, in the better part of a year, in numbers a human life can comfortably hold. Jupiter quietly retires that unit. From here outward, the natural measure of a voyage is the year, and then the decade, and the comfortable mental arithmetic you started this journey with is gone for good. Jupiter is the first of the giants, a world so large that all the other planets in the solar system could be packed inside it with room to spare, and reaching it is the moment the solar system stops feeling like a neighborhood and starts feeling like an ocean. The reason we want so badly to go is not really Jupiter itself, enormous and stormy as it is. It is Jupiter's moons, 3 of them in particular, named Europa, Ganymede, and Callisto, are among the most extraordinary places we have ever discovered. Each of them very likely hides beneath a frozen crust of ice, a global ocean of liquid water, not a lake, not a sea, but a world-spanning ocean wrapped all the way around the moon, kept from freezing by a process called tidal heating, in which Jupiter's immense gravity constantly flexes and squeezes the moon's interior, and that endless kneading generates heat from the inside. The ocean beneath Europa's ice is estimated to hold more liquid water than every ocean on Earth combined. Its frozen surface is cracked and laced, with long fracture lines that hint at a restless, moving shell, and that surface even generates a thin whisper of oxygen, produced as radiation breaks apart the water ice. If we are searching for life somewhere other than Earth, Europa is the single most credible address we currently possess. There may be, right now, a sunless ocean under that ice, warm and salty and old, and we have no idea what is in it. And Europa is only one of the three. Ganymede, another of Jupiter's great moons, is the largest moon in the entire solar system, larger even than the planet Mercury, and it too appears to hide an ocean beneath its ice, and stranger still, it generates its own magnetic field, the only moon known to do so. Callisto, the outermost of the three, is the most heavily cratered object we know, an ancient battered face that may also conceal a buried sea beneath its surface. 3 moons, 3 possible oceans, 3 sunless seas wrapped around 3 different worlds, all of them circling a single planet. When the astronomer who first turned a telescope on Jupiter 4 centuries ago saw these little points of light shifting night by night, he had no way of knowing he was looking at what may turn out to be the most promising real estate for life in the entire solar system. We have known they were there for 400 years. We have only just begun to learn what they actually are. What keeps those oceans liquid, so far from the sun's warmth, is the same force that makes the whole system so deadly. Jupiter's gravity is so immense that it does not merely hold its moons. It needs them, stretching and squeezing their interiors as they orbit, and that endless flexing generates heat from the inside, enough to keep entire oceans from freezing. But that same gravity, that same restless energy, drives ferocious belts of radiation around the planet, regions where charged particles are trapped and accelerated to lethal intensity. The very thing that warms the oceans poisons the space around them. Jupiter is a place where the conditions that might create life and the conditions that would instantly destroy a visitor are produced by one and the same engine. Jupiter sits somewhere between about 590 million and 970 million kilometers from Earth, depending on where the 2 planets are in their orbits. At an average distance, the light from Jupiter takes about 43 minutes to reach us, and the travel time split, once again, exactly along the line we have been drawing all night, the line between flying past and stopping. The fast flybys are genuinely fast, for such a distance. The first spacecraft to reach Jupiter, called Pioneer 10, got there in about 640 days, roughly 21 months, on a fairly direct path. The spacecraft, Voyager 1, did it in about 546 days. But those missions did not stop. They came, they swept past in a matter of days, they gathered what they could, and they kept going, flung onward by Jupiter's own gravity toward the farther planets. To actually stop at Jupiter, to enter orbit and stay, is a completely different and far slower undertaking, and the spacecraft Galileo is the proof. Galileo launched in 1989, and it took nearly 6 years to settle into orbit around Jupiter. It did not take 6 years because it was slow or weak. It took 6 years because arriving at Jupiter too fast means flying helplessly past it. Exactly the Mercury problem all over again, just colder and farther out. To bleed off enough speed to let Jupiter's gravity capture it, Galileo flew a long, looping path, swinging once past Venus and twice past Earth, gathering and shaping its velocity so that it would arrive not fast and triumphant, but slow and catchable. A later spacecraft called Juno, which is still circling Jupiter today and returning remarkable measurements of the planet's magnetic field and hidden interior, launched in 2011 and arrived in 2016, a journey of about 5 years. And now, as you listen to this, a spacecraft is in the middle of exactly this kind of journey. It is called Europa Clipper, and it launched in October of 2024, built for the single purpose of studying that ocean moon. Picture its path, because it is a perfect portrait of how the machine actually works. It does not fly straight at Jupiter. In the spring of 2025, it swings back inward and skims just a few hundred kilometers above the surface of Mars, stealing a little of that planet's motion. Then it loops back out toward Earth at the end of 2026 for a second gravity assist, borrowing again from the world that launched it. Only then slung forward by these careful thefts of momentum, does it finally coast outward to arrive at Jupiter in the spring of 2030, a transit of about 5.5 years. And even once it arrives, it will not orbit Europa directly, because the radiation around that moon is so violent it would destroy the spacecraft's instruments within weeks. Instead, it will loop around Jupiter on a wider, safer path, and dart in close to Europa again and again, dozens of times across roughly 4 years, snatching its measurements in brief passes and then retreating to safety before the radiation can kill it. Picture what one of those passes is actually like for the spacecraft. It comes sweeping in from its wide, safe loop around Jupiter, accelerating as the moon's gravity draws it nearer, and for a few precious hours Europa fills its view, a cracked and frozen world, veined with long reddish lines, smoother than almost anything else in the solar system because the ice is constantly renewing itself from below. Every instrument runs at full capacity, mapping the ice, sounding for the ocean beneath, sniffing the thin haze of oxygen, drinking in as much as it possibly can. And then, before the radiation can accumulate to a fatal dose in its electronics, it must flee, climbing back out to the safety of its distant orbit to recover, to send its data home, and to wait for the next pass. Dozens of times it will do this, approaching and retreating, gathering its portrait of that ocean moon, one careful glance at a time, because to stay would be to die. It is reading a book by lightning, a page at a time, in the few seconds each flash allows. That detail is worth sitting with, because it shows you how hostile this part of the solar system truly is. The most promising place to look for life that we have ever found is wrapped in radiation so lethal that even our robots cannot linger there. Near Europa, an unshielded human being would absorb a fatal dose in something like 10 minutes. And shielding a human against it means carrying heavy shielding, and heavy shielding means more mass, and more mass means more propellant, and more propellant means a longer, slower trip. And so the problem compounds in every direction at once, each difficulty feeding the next. This is why a human mission to Jupiter's moons is not on any honest near-term horizon. It is not cowardice, and it is not lack of imagination. It is the brutal arithmetic of the machine, stacked higher than anywhere we have yet stood. Jupiter stretches the very definition of what reachable means, and the next world out, the ringed one, stretches it further still, and then rewards the wait with 13 years of wonder that we are, in a real sense, still living inside. Part 7. Saturn and the spacecraft that stayed. Saturn is the world that makes the case, more powerfully than any other, that the long wait is worth it. Everything about Saturn argues for patience. It is farther than Jupiter, harder to reach, harder still to stop at, and the spacecraft that finally did stop there gave back something so extraordinary that it quietly justified every year of the journey and then a great many years more. To understand Saturn is to understand why a species would willingly spend 7 years travelling to a place in order to spend 13 years there. Begin with the rings, because they are stranger than their beauty lets on. The ring system of Saturn spans about 282,000 kilometres from its inner edge to its outer edge, a span wide enough that you could nearly line up 22 Earths across it. And yet, for all that breadth, the rings are astonishingly, almost impossibly thin. On average, they are only about 10 metres thick. Try to hold those two facts in your mind at the same time, because they do not want to coexist. If you shrank the rings of Saturn down until they were as thin as a single sheet of paper, that sheet of paper would still be about 5 kilometres wide. A film of ice and rock stretched across 250,000 kilometres and almost nothing in the other direction. How a structure like that forms, how it holds itself together against the constant pull that should tear it apart, and when it will eventually fade and disperse, are questions we still cannot fully answer. The rings may be far younger than the planet. They may be slowly raining down into Saturn even now. We are, in a sense, lucky to be alive at a moment when they are here to see it all. There is a humbling possibility hidden in those rings, one that touches on time itself. For a long while, it was assumed the rings were as old as Saturn, a permanent feature billions of years in the making. But the evidence increasingly suggests they may be far younger, perhaps only a few 100 million years old, which, in the life of a planet, is practically yesterday. They may have formed when some icy moon wandered too close and was torn apart by Saturn's gravity, its shattered body spread into the brilliant disk we see. And just as they may be young, they may be temporary. The rings appear to be slowly raining down into the planet, drawn inward grain by grain, fading on a timescale that, while long by human reckoning, is brief against the age of the solar system. If that is true, then the rings did not exist when the earliest life on Earth was taking shape, and they may be gone long before our sun dies, which means we are alive in the narrow window when they happen to be here, looking up at a feature of the sky that is, in cosmic terms, just passing through. There is something almost unbearably fortunate about that, to exist in the brief age when Saturn wears its crown. But the rings are only the entrance. Saturn's moons are the reason the wait pays off. Titan, the largest of them, is a world with weather, with a thick golden atmosphere of nitrogen, and beneath that haze, lakes and rivers and seas, not of water, but of liquid methane and ethane, cold enough to flow like our rivers do, but made of what we would call natural gas. Titan has a chemistry so rich and so strange that serious scientists ask, without embarrassment, whether some form of life, utterly unlike our own, could exist in those frigid hydrocarbon seas. And then there is Enceladus, a small, bright, icy moon that does something almost generous. From long cracks at its south pole, Enceladus sprays plumes of water vapor and salt and organic compounds directly out into space, fountains rising hundreds of kilometers above the surface. That spray comes from a hidden ocean beneath its ice, which means Enceladus is, in effect, handing out free samples of its buried sea to any spacecraft willing to fly through the mist. It is offering us the inside of itself, and all we have to do is be there to catch it. There is a moment from Cassini's mission that deserves to be told on its own, because it is one of the most quietly astonishing things our species has ever done. Cassini did not travel to Saturn alone. It carried a small probe called Huygens, built to do something almost unthinkable. After arriving, Cassini released that little probe toward Titan, and Huygens fell through that thick golden haze for 2.5 hours, parachuting down through an alien sky no eye had ever pierced, sampling the air as it descended, until it touched down softly on the surface of a moon of Saturn, more than 1 billion kilometers from home, and kept transmitting from the ground. It remains the most distant landing human beings have ever achieved. A machine built on Earth came to rest on the frozen shore of a methane sea in the outer solar system and sent back the view. Let that sit beside the travel times for a moment. We did that once more than 1 billion kilometers away, and most people have never heard its name. On Titan, the seasons themselves run on a timescale that dwarfs a human life. Saturn takes about 29 Earth years to circle the Sun once, which means a single season on Titan lasts more than 7 of our years. Cassini stayed long enough to watch those slow seasons turn, to see methane clouds gather and methane rain fall, and the great hydrocarbon lakes shift with the changing light. To study weather on Titan is to commit to watching something that changes more slowly than a human childhood, and Cassini, by staying for 13 years, saw enough of it to begin to understand. That is the gift that only patience buys, and it is the reason the wait is the whole point. Getting there is the familiar, long story. The earlier spacecraft Pioneer 11 reached Saturn after about 6.5 years. Voyager 1 riding a favorable alignment, made it in just over 3 years. Voyager 2 took about 4. But those were flybys, glimpses through the window. The mission that stopped, the mission that stayed, was called Cassini, and its journey is the clearest illustration tonight of what stopping truly costs and truly buys. Cassini launched in 1997, and it did not arrive at Saturn until 2004, 7 years in transit. And it spent those 7 years not flying straight, but threading a long chain of gravity assists, swinging past Venus twice, then past Earth, then past Jupiter, each pass carefully shaping its speed, all so that when it finally reached Saturn, it would be moving slowly enough to be captured, rather than fast enough to be lost. 7 years of patience, purchased entirely to arrive at the right velocity, and then Cassini stayed. For 13 years it circled Saturn, looping among the moons, flying through the plumes of Enceladus, dropping a small probe down through the haze of Titan to the surface below, watching the seasons turn on a world where a single season lasts more than 7 Earth years. 13 years of discovery, returned by a machine that had spent 7 years simply getting there, and when its fuel finally began to run low, the people who flew it made a remarkable choice. Rather than let Cassini drift and eventually crash uncontrolled, possibly contaminating Enceladus or Titan with microbes from Earth, possibly poisoning the very oceans it had taught us to dream about, they decided to destroy it deliberately, cleanly, on their own terms. Picture the end of it. It is September of 2017. Cassini, after 20 years of flight, turns toward the cloud tops of Saturn for the last time. It points its antenna back toward Earth and holds it there, steady, refusing to look away, transmitting everything it can sense for as long as it can. It begins to fall into the upper atmosphere of the planet it has circled for 13 years. The thin gas begins to tear at it, and the spacecraft fires its small thrusters harder and harder, straining to keep its antenna locked on the distant point of light that is home, still sending, still describing the air around it as that air destroys it. And then, more than an hour after it actually happened, because that is how long the final signal took to cross the gulf back to us, the data simply stops. In a control room on Earth, people who had given decades of their lives to this machine watched the line go flat, and many of them wept, because something that was not alive had nonetheless been with them for a very long time, and now it was gone. There is a detail in that ending that says something true about why we do any of this. The people who chose to destroy Cassini did not have to. They could have let it run out of fuel and drift, becoming a dead piece of debris circling Saturn for ages. Instead, they chose the deliberate plunge precisely because they had come to care about the worlds Cassini discovered. A drifting, uncontrolled spacecraft might one day have crashed into Enceladus or Titan, carrying with it hardy microbes that had stowed away from Earth, contaminating the very oceans that might harbour life of their own. So, they decided to sacrifice their spacecraft to protect those oceans, to keep them pristine for some future mission that might one day go looking for what lives there. It was an act of stewardship across time, a choice made on behalf of discoveries that have not happened yet. And when the final signal faded, the people in that control room, scientists and engineers, who had given 20 years of their working lives to a single machine, stood and wept and embraced one another, grieving for something that was never alive, but had, across 2 decades, become a companion. A machine can earn that kind of love. The length of the journey is part of how it earns it. Cassini's measurements are still being studied today, years later. In every way that matters, we have not finished being at Saturn. We are still there, and that is the answer to anyone who asks whether a 7-year journey could possibly be worth it. Beyond Saturn, though, the solar system becomes something else entirely, a place we have barely touched, where 2 enormous worlds have each been visited exactly once by the same lonely spacecraft in the same brief decade. Part 8. The Ice Giants, seen once and then never again. Beyond Saturn lie two worlds that most planetary scientists rank among the highest priorities in their entire field, and that between them have received exactly one close visit each, both from the same single spacecraft, both within the same handful of years in the 1980s. After that, nothing. No one has been back. No one is there now. And the soonest anyone could be is so far in the future that many of the scientists who most want to go will not live to see the data arrive. These are Uranus and Neptune, the ice giants, and their story is the story of how distance can turn into a kind of abandonment, not through neglect, but through the plain arithmetic of how long it takes to get there. They are called ice giants to set them apart from Jupiter and Saturn, and the distinction matters. Jupiter and Saturn are built mostly of hydrogen and helium, the light gases. Uranus and Neptune are built around something denser, a thick, hot, high-pressure fluid of water, methane, and ammonia, the materials we loosely call ices, even though they are nothing like the ice in your freezer. And here is the reason this obscure category should matter to you. When we look out at the planets orbiting other stars, across the whole galaxy, the single most common type of world we find is not a Jupiter and not an Earth. It is a planet in this in-between size range, larger than Earth and smaller than Neptune, which means that Uranus and Neptune, the two planets in our own solar system we understand the least, are our closest examples of the most common kind of planet in the galaxy. To understand how they formed is, in part, to understand the most ordinary worlds in the universe, and we have studied them for a total of a few hours each. Uranus alone is a catalogue of mysteries. It is tipped over on its side, its axis tilted about 98 degrees, so that rather than spinning upright like a top the way the other planets do, it rolls around the Sun like a ball, its poles taking turns pointing almost directly at the Sun across its long orbit. Its magnetic field is bizarre, tilted nearly 60 degrees away from its spin axis and shoved off to one side, not centered on the planet at all, but displaced by about a third of the planet's radius, as though something inside it is deeply out of true. And alone among all the giant planets, Uranus gives off almost no internal heat of its own, a strange coldness that may be the lingering scar of some colossal, ancient collision that knocked it sideways and disrupted the way heat moves through its interior. Every one of these facts is a thread we cannot pull because we have no spacecraft there to pull it. Everything we know up close about both of these worlds comes from a single source. The spacecraft Voyager 2 flew past Uranus in January of 1986 and past Neptune in August of 1989, and then continued on out of the solar system forever. Those two brief flybys, a few hours of close observation each, are still essentially the entire library of intimate knowledge we possess about two giant planets. And the only reason Voyager 2 could visit both was a rare gift of timing. Roughly once every 176 years, the outer planets line up in an arrangement that lets a single spacecraft chain gravity assists from one to the next, riding the relay all the way out. Voyager 2 was launched in 1977 specifically to catch that alignment, and catch it did. The trip of several lifetimes, flown once and not repeatable for well over a century. Sit for a moment with the strangeness of that arrangement, because it is genuinely without parallel in how we explore. Imagine that everything humanity will ever know, intimately, about two entire worlds had to be gathered during a few hours each, by one machine, passing once, decades ago, and then never again in your lifetime, or perhaps your children's. We have orbited Mars for years, and circled Saturn for over a decade, and flown a probe around Jupiter again and again. But Uranus and Neptune we met only in passing, two brief encounters at the end of the 1980s, like two faces, glimpsed once through the window of a train that did not stop and will not come back this way for a very long time. Everything we say about them with confidence, every textbook diagram, every fact, traces back to those few hours. It is the thinnest thread of knowledge connecting us to two of the largest worlds in our own solar system, and it has not been added to in over 30 years. There is a plan to return, and its timeline tells you everything about the distances involved. The next dedicated mission, a spacecraft built to orbit Uranus and drop a probe into its atmosphere, has been ranked the single highest priority for new outer solar system exploration in the most recent survey of the field. The best launch opportunities fall around the year 2031 or 2032, and even using a gravity assist from Jupiter to help it along, the cruise to Uranus would take roughly 13 years. Which means that if everything goes well, if the mission is funded and built and launched on time, the first close measurements of Uranus since 1986 would begin arriving sometime around the middle of the 2040s. And there is a sobering complication, current as of right now. The funding may not arrive in time to use that Jupiter assist window at all, and without Jupiter's help, the trip stretches longer still. That is not a failure of will. It is an honest accounting of what the machine demands. Neptune, when Voyager 2 finally reached it, turned out to be no quieter than its sibling. It is the windiest world in the solar system, with storms that howl at speeds approaching 2,000 kilometers per hour, faster than the speed of sound on Earth, raging across a planet so far from the Sun that it receives only 1,000th of the sunlight we do. Where that energy comes from, on a world so cold and so dim, is still not fully understood. And circling Neptune is a moon called Triton, which orbits backward against the direction of the planet's spin, a sign that it did not form there at all but was captured, snatched long ago from the population of icy bodies at the solar system's edge. Triton has geysers, plumes of nitrogen erupting from its frozen surface, and it is slowly spiraling inward, doomed across the ages to be torn apart by Neptune's gravity into a ring. All of this, every word of it, we know from a few hours of one flyby in 1989. Everything that has happened on Triton since then, we have simply not seen. Neptune is farther yet, and its situation is harder. A direct trajectory to put a spacecraft in orbit around Neptune, flown with the propulsion we actually have, runs something like 12 to 15 years, and there is no upcoming planetary alignment on the horizon that would recreate the lucky chain Voyager 2 exploited. The science case for going is overwhelming. The path for getting there is simply not yet clear. So this is where we stand with the ice giants. Two of the most important worlds in the galaxy's most common category, sitting in our own solar system, known to us from a few hours of one spacecraft's attention more than 3 decades ago, with the next real visit, if it happens at all, sending its first answers back to a generation not yet grown, and still we are not at the edge. There is one more world to reach, the small frozen one at the far rim, the one we visited exactly once, briefly, and which surprised everyone who saw it. Part 9. Pluto, the afternoon at the edge. Pluto sits at the outer edge of the worlds we have managed to reach, and the numbers attached to it are the largest of our whole journey, the place where months and years finally give way to the better part of a decade for a single glance. Pluto orbits the Sun on a long, tilted, oval path that carries it between roughly 4.4 billion and 7.4 billion kilometers from Earth, depending on where both worlds sit. The distances are so enormous that even light, which crossed to Mars in 12 minutes and to Jupiter in 43, now takes between about 4 and 7 hours to make the trip one way. Sit with what that does to the very idea of control. If you send a command to a spacecraft at Pluto, that instruction travels for 4 to 7 hours before it arrives, and any confirmation that it was received travels 4 to 7 hours back. A simple round-trip exchange can take most of a day. You cannot fly a spacecraft at Pluto in any live sense. You cannot react to what it sees. Everything it does must be written in advance, loaded into its memory, and trusted to unfold on its own, hours beyond the reach of any human hand. The machine, out here, must fly itself. The spacecraft that made the journey was called New Horizons, and there is a poignancy in how small it was for so vast a task. It weighed only about 478 kilograms, roughly the mass of a large motorcycle, a modest little package of instruments flung toward the rim of the known solar system. It launched on the 19th of January, 2006, and to give it any hope of reaching Pluto within a human career, it was launched faster than anything before or since. New Horizons left Earth at about 58,500 kilometers per hour, the fastest launch speed ever given to a spacecraft, fast enough to cross the distance to the Moon in a matter of hours rather than days. Then, in February of 2007, it swung past Jupiter and stole a portion of that giant's momentum, a gravity assist that shaved roughly 3 years off its journey. And even moving that fast, even with that boost, it did not arrive at Pluto until the 14th of July, 2015, 9.5 years for the fastest thing we ever launched to reach the edge. And here is the part that makes this whole survey ache a little. After 9.5 years of flight, New Horizons did not stop. It could not. It was moving far too fast, and Pluto, small and low in gravity, could never have captured it. To slow down enough to enter orbit around Pluto would have required carrying braking fuel with a mass roughly 4 times the entire mass of the spacecraft itself, an utterly impossible amount to launch. So New Horizons was built from the start as a flyby, a single pass, one chance. Picture that moment, the payoff of a decade of patience compressed into a few hours. The spacecraft comes screaming in toward Pluto at tens of thousands of kilometers per hour, its cameras and instruments running at full capacity, drinking in everything they can as the world swells in the view and then begins, already, to shrink behind it. There is no second look. There is no lingering. A decade of travel, and the close encounter itself is essentially a single afternoon, and then Pluto is falling away into the dark behind a machine that can never turn around. And Pluto, it turned out, was not even the end of the road, but the doorway to a whole region we had barely understood. Out at that distance, Pluto is not alone. It is the brightest member of an enormous belt of frozen worlds, thousands upon thousands of icy bodies orbiting beyond Neptune in a band we had only recently learned was there. After its single afternoon at Pluto, New Horizons kept going, still falling outward, and a few years later, on the first day of 2019, it flew past a small, reddish, two-lobed object far beyond Pluto, a frozen fragment left almost untouched since the birth of the solar system, the most distant world any spacecraft has ever examined up close. The edge, in other words, kept receding. Every place we thought was the boundary turned out to be a threshold with more beyond it, and New Horizons is still out there now, still moving, still sending back its faint signal across a gulf that grows wider every day. There is a loneliness to operating a spacecraft that far away that is worth feeling for a moment. With the round trip for a signal stretching across most of a day, the people who fly New Horizons cannot react to anything in real time. When the spacecraft swept past Pluto, the entire encounter was choreographed in advance, every camera turn and every measurement written into its memory months earlier, and then the team on Earth simply had to wait, helpless and hopeful, while a machine they could no longer reach carried out the most important hours of its life entirely on its own. They did not even know if it had survived the pass until its signal, sent automatically, finally crossed the hours of space back to them. To explore the edge of the solar system is to let go of control completely, to build something patient and clever and brave, and then to send it beyond the reach of your own hands and trust it to do the work alone. What that afternoon revealed rewrote the textbook. Everyone had expected Pluto to be a dead, cratered, frozen relic, a lump of ice with nothing to say. Instead, New Horizons found a world that is quietly, astonishingly alive. There are glaciers of frozen nitrogen actually flowing and churning across its surface, slow rivers of ice that erase old craters and renew the ground. There are mountains made of water ice, hard as rock at those temperatures, rising as high as 3,500 meters. There is a thin nitrogen atmosphere that freezes and falls as a kind of snow during Pluto's centuries-long winter, then lifts again as it slowly warms. There are surface features that point to geological processes still at work. On a body at the very rim of the Sun's family, a place that by every reasonable expectation should have frozen solid and gone still billions of years ago. Pluto, the world we visited for a single afternoon after 9.5 years of travel, turned out to be one of the most surprising places we have ever seen. Hold the image of that single afternoon a little longer, because it is the emotional center of this entire journey outward. 9.5 years of travel. 9.5 years of a small machine falling through the dark, its makers waiting and aging back on Earth, the launch a fading memory by the time of arrival. And the reward for all of it was a few hours of clear, close looking, the cameras working at their limit, gathering every photograph and measurement they could before the geometry pulled Pluto away again. There was no slowing to savor it. There was no orbit, no second pass, no lingering over the most beautiful views. The spacecraft was already leaving as it arrived, carried by the same speed that had made the whole trip possible in the first place. It is a kind of poem about longing, written in orbital mechanics. You can spend a decade of patience and ingenuity reaching for something at the edge of everything, and what you are granted, in the end, is a single afternoon of clear sight, and then the long falling away. And remarkably, that single afternoon was enough to overturn everything we thought we knew about that distant little world. There is at present no mission in active development to return to Pluto. And if we ever wanted to send people, the numbers become almost unreal. A crewed mission to Pluto with the chemical propulsion we have today would require something like 35 years of travel in one direction. 35 years is not a mission, it is a generation. The crew who launched would not be the crew who arrived. Children would be born and grow to adulthood in transit. With the advanced nuclear propulsion concepts that exist so far only on paper and in early experiment, that span might be compressed to perhaps 15 or 20 years, which is to say, still most of a working life, spent crossing the dark to glimpse a world we have already seen for one afternoon. Out here at the edge, the true shape of the problem finally stands fully revealed, and it is time to name the single fact that has been hiding underneath every planet we have visited tonight, the fact that secretly explains them all. Part 10. The hidden rule that explains everything. There is one truth running underneath this entire journey, and it deserves to be said plainly rather than softened, because once you see it, every number we have walked through tonight suddenly makes sense at once. The limiting factor for almost every mission we have discussed is not getting there fast, it is stopping. Going is the easy part. Stopping is the thing that breaks us. Everything else, every long delay, every looping 6-year path to a planet a faster craft flew past in months, is downstream of that single, stubborn, almost unfair fact. Think about why. On Earth, when you want to stop a moving thing, the world helps you. There is air pushing back. There is friction between tire and road. There are brakes that turn motion into heat and bleed it away. You are surrounded by things to push against, and so slowing down feels free, automatic, the natural tendency of everything. Space is the exact opposite. Space is empty. There is nothing to push against, nothing to rub against, nothing to bleed your speed away into. Once you are moving, you keep moving, perfectly, forever, until something stops you. And the only thing that can stop you is the same thing that got you moving in the first place. You have to fire an engine in the opposite direction, and firing an engine means burning propellant. Slowing down by a certain amount costs you exactly as much fuel as speeding up by that same amount once did. Braking, in space, is not the absence of effort. It is effort run in reverse, and it is just as expensive. Now follow that fact where it leads, because it compounds in a way that is genuinely vicious. Every kilogram of braking fuel you intend to burn when you arrive, you must first carry the entire way there. And to carry it, you must lift it off the surface of Earth, up out of our planet's own gravity, which takes fuel. Then you must accelerate it across hundreds of millions of kilometers along with the rest of your spacecraft, which takes more fuel, and only then, at the very end, do you finally burn it against your own momentum to slow down. So the fuel you need to stop demands more fuel to carry it, which demands more fuel to carry that, and the whole requirement climbs not gently but exponentially, faster and faster the more performance you ask for. This relationship was written down more than a century ago, long before anyone had launched anything, by a quiet Russian schoolteacher working out the mathematics of rockets that did not yet exist. He realized, with nothing but pencil and paper, that because a rocket has to carry and accelerate its own unburned fuel, the demands grow not in step with the speed you want, but far faster, in the punishing way that compounding always grows. It was a discovery made in pure theory, and every spacecraft since has been forced to obey it. The dreamers, who imagine effortless travel between the worlds, are not wrong about the destinations. They are forgetting the schoolteacher's arithmetic, the iron bookkeeping that has shaped every real mission we have ever flown. This is the iron law that sits at the center of all space travel. Wanting to arrive a little faster does not cost a little more. It can cost catastrophically more until the rocket you would need is larger than anything that could ever leave the ground. Let yourself stand inside that arithmetic for a moment, because it is stranger and more vivid than any equation makes it sound. You are aboard a spacecraft that left Earth years ago. For all that time you have been falling, silent and engineless, along a curve through the dark, carrying with you a great reserve of fuel that you have not been allowed to touch. You have guarded it across hundreds of millions of kilometers. You have protected it the way you would protect water in a desert. And now the destination finally rises in your window, growing from a point of light into a disk, into a world, and every cell in your body wants to arrive, to coast in gently, to let the long trip simply end. But the universe does not offer gentle arrivals. If you do nothing, you will fall straight past this world and back into the endless dark, the years of travel wasted. So at the exact instant of arrival, the moment of triumph, you must turn your engine to face forward, to face the very direction you are racing, and you must fire it with everything you saved, spending all of it at once, not to go anywhere, but only to stop. You burn your entire reserve, fighting against your own speed, against the momentum that carried you here, just to win the right to stay. The whole journey ends not with a flourish, but with a desperate, expensive act of restraint. There is something almost absurd about it, and something beautiful too. The hardest part of going to another world is convincing the universe to let you stop when you get there. This compounding has a name and a shape, and it is worth seeing it clearly because it is one of the most important and least known facts about why we are still so confined. The relationship between how much speed a rocket can gain and how much fuel it must carry is not a straight line. It is a curve that bends upward ever more steeply, so that each additional increment of velocity costs disproportionately more fuel than the one before it. To go a little faster, you carry somewhat more fuel. To go faster than that, you carry dramatically more. To go faster still, the fuel required runs away toward absurdity, because you are now carrying fuel to carry the fuel to carry the fuel. This is the reason rockets are almost entirely fuel by weight, great towering tanks with a tiny payload perched on top. The useful part, the part you actually want to send somewhere, is a sliver. Almost everything else is propellant, and most of that propellant exists only to lift the rest of the propellant. Once you understand that curve, the entire shape of human spaceflight snaps into focus. It is why we have stood on the moon, but not on Mars. It is why our spacecraft to the outer planets are small and light and unmanned, packages of instruments rather than habitats for people. It is why nearly every interplanetary mission chooses the slow, cheap, coasting path and the long detours through gravity assists, not out of caution but out of necessity, because the fast path would demand a quantity of fuel that no rocket could lift. We are not slow because we lack ambition. We are slow because the mathematics of carrying our own brakes punishes speed with a cruelty that grows the harder we push. The curve is the cage. This single rule explains the whole survey, every strange number. It is why Messenger needed 6.5 years to reach Mercury when Mariner 10 flew past in 6 months. It is why Galileo needed nearly 6 years to fall into orbit around Jupiter. It is why Cassini spent 7 patient years in transit to Saturn before it could take a single measurement from orbit. It is why every serious engineering study of a crewed Mars mission keeps returning the same 7 to 9 month transit time, no matter how much we wish otherwise, because shortening it would demand a higher thrust engine, and a high thrust engine powerful enough to carry people at flight-ready maturity does not yet exist. The reason we measure these journeys in years and decades is not that the universe forbids us to go faster. It is that going faster means stopping harder, and stopping harder means a mountain of fuel we cannot yet carry. The wall is not distance. The wall is the brakes. And that raises the only question that really matters about our future out here. Could that ever change? Is the wall permanent? Or is it simply a wall we have not yet learned to climb? Part 11. The engine we have not built. The honest answer to whether these travel times could ever shrink is yes, in principle, and the reason they have not yet is more a story about choices than about physics. There is no law of nature that locks us into 7-month crossings to Mars and 9-year crawls to Pluto. There are, on paper and in early experiment, kinds of engines that could cut those times dramatically. The reason we still fly the slow way is that we have not yet built and flown the fast way, and understanding why is the final piece of tonight's picture. Everything we have launched in this entire survey runs, fundamentally, on chemical propulsion, the same basic idea as a firework, burning fuel and oxidizer together, and throwing the hot exhaust out the back. Chemical rockets are powerful and reliable, and we understand them deeply, but they are bumping against a ceiling set by chemistry itself. There is only so much energy you can wring out of a chemical reaction per kilogram of fuel, and we are already near that limit. To go meaningfully faster, you do not need a better chemical rocket. You need to stop relying on chemistry altogether and reach for something far more energetic, and the most mature candidate is nuclear. The first version is called nuclear thermal propulsion. The idea is elegant. Instead of burning fuel, you use a nuclear reactor to heat a propellant, usually hydrogen, to an extreme temperature, and then blast that superheated gas out the back. Because you are not limited by the energy of a chemical reaction, only by how hot you can make the gas before it melts your engine, you can get roughly twice the efficiency of the best chemical rockets. Twice. The efficiency does not sound dramatic until you remember how exponentially the fuel requirements climb. In principle, a nuclear thermal engine could cut the crossing to Mars from 7 to 9 months down to something like 3 or 4, and in doing so, it would slice the radiation dose and the bone loss and half the danger of the trip along with it. The technology is not science fiction. Versions of it were built and tested on the ground decades ago, but no nuclear thermal engine has ever actually flown in space and carried out a real mission, and there is the gap. And here the story takes a turn that the optimistic version usually leaves out, a turn that is current as of right now. For the last few years, the flagship effort to finally fly a nuclear thermal engine was a joint project between the American Defense Research Agency and the Space Agency, a demonstration designed to put a working reactor engine in space within a few years. In 2025, that project was cancelled. The funding for it was zeroed out. The reasons given were partly that the cost of ordinary chemical launches had fallen so steeply that some of the old advantages looked smaller, and partly an analysis suggesting that a different approach, a slower but even more efficient kind of nuclear engine, might be the wiser, long-term bet. Whatever the merits of that decision, the plain fact is that the single most advanced near-term effort to break the speed barrier we have been describing all night was just shut down. The engine that could halve the trip to Mars is, once again, not being built at the scale the problem demands. There is a way to measure how good a rocket engine is at stretching its fuel, and it makes the nuclear advantage concrete. Engineers talk about efficiency in terms of how much push you get from each unit of propellant, and by that measure, a good chemical rocket is already near the best that chemistry allows. A nuclear thermal engine, by heating its propellant far hotter than any chemical flame, roughly doubles that figure. Doubling does not sound like much until you remember the runaway curve we just described, where every gain in efficiency pays off enormously in how much less fuel you must carry. A doubling at that lever is the difference between a Mars trip that takes the better part of a year and one that takes a third of that. And the strange part is that this is not a new dream. Engines of exactly this kind were built and fired on test stands on the ground more than half a century ago, glowing and roaring and proving the concept worked, and then the programs were cancelled before any of them ever flew. We have known how to do this, in principle, for 50 years. We have simply never carried it through. That other approach, the one the analysis favoured, is called nuclear electric propulsion, and it works on a completely different rhythm. Instead of heating and blasting propellant in a great rush, it uses a reactor to make electricity and uses that electricity to fling charged particles out the back, very gently but very efficiently, a whisper of thrust sustained for years on end. It produces almost no push at any given instant, far too little to lift off a planet, but in the patience of open space, where there is nothing to slow you and all the time in the world to accelerate, that endless gentle shove can build up to tremendous speeds while sipping fuel. For the outer planets, where the journey is dominated not by the launch but by the long, long cruise, that kind of engine could be transformative. And like its nuclear thermal cousin, it exists today only in prototype and early developmental forms. Neither kind of engine has ever been certified to carry human beings. There are other ideas farther out on the horizon, gentler and stranger, that hint at how much room there still is to grow. There are concepts for sails, vast and mirror-thin, that would catch not wind but the faint pressure of sunlight itself, or the push of a powerful beam of light fired from home, accelerating a feather-light craft to speeds no rocket could reach, precisely because such a craft would carry no heavy fuel at all. None of these is ready to carry the mass of a real science payload, let alone a human being, and some may never leave the page. But they matter as a reminder that the slowness we have described all night is not a verdict from physics that the case is closed. It is a snapshot of where we happen to stand with the engines we happen to have built. The ceiling is real, but it is a ceiling in this room, not a ceiling on the sky. So this is the real shape of our situation, and it is worth seeing clearly without either despair or false comfort. The reason a trip to Mars takes the better part of a year, the reason Pluto takes a decade, the reason the ice giants sit unvisited for generations, is not a hard wall written into the universe. It is an engine we have not yet committed to building and flying. The capability is within reach. The physics permits it. What is missing is the sustained decision to close the gap, and closing that gap is arguably the single most important investment in the human future in space that is not currently being made at the scale it deserves. It is worth being honest about what kind of barrier this really is, because it changes how you should feel about everything we have traced tonight. There are barriers in nature that are absolute, written into the laws of the universe, that no amount of cleverness can ever cross. The speed of light is one of those. But the travel times in this survey are not that kind of barrier. They are not a law of nature telling us no. They are a snapshot of a choice we have not yet made, a capability we have not yet committed to building at the scale it would take. The difference matters enormously. If the slowness were a law of physics, there would be nothing to do but accept it. But it is not. It is a gap between what is possible and what we have chosen to fund and fly, and that gap is exactly the kind of thing a determined generation can close. The reason a journey to Mars still costs a crew most of a year and a dangerous dose of radiation is not that the universe demands it. It is that we have not yet built the engine that would change it, even though we have known how, in principle, for half a century. The wall, in other words, is partly of our own making, and that should not leave you discouraged. It should leave you with a strange kind of hope, because a wall we built ourselves is a wall we can choose to take down. Which brings us, finally, to the question underneath all the others. If the trips are this long, this costly, this hard, then why go at all? Part 12. Why the trip was always worth making. The slow pace of all of this, the years and the decades, the cancelled engines and the unvisited worlds, could leave you with the feeling that the whole enterprise is hopeless, that we are too small and the distance is too large and the brakes too expensive ever to really matter. I want to leave you with the opposite feeling, because the actual record of what these long, patient, maddening journeys have given us argues powerfully the other way. The slowness has never made the effort pointless. If anything, the slowness is the measure of how precious each arrival has been. Consider what every single one of these journeys returned, no matter how long it took. Mariner 10 gave us our first close look at the cratered face of Mercury, a world no human eye had ever resolved. The Venera landers gave us 127 minutes on the surface of Venus, the only minutes we have ever had, photographs from inside a furnace that no machine has matched since. The Viking landers gave us the first chemistry of Martian soil, the opening move in a search for life that continues to this day. Galileo gave us the measurement that revealed Europa's hidden ocean, more water than all of Earth's seas, sealed beneath the ice. Cassini gave us the discovery that little Enceladus is actively spraying the contents of a buried sea into space, an invitation we are still learning how to accept. New Horizons gave us a Pluto that is geologically alive, glaciers and mountains and snow at the edge of everything, where we expected only a frozen stone. Not one of those discoveries required the journey to be fast. Every one of them required only that the journey be made. And notice that the discoveries were almost never the ones we expected. We did not send New Horizons to Pluto expecting to find flowing glaciers and snowfall and a world still alive. We did not send Cassini to Saturn knowing that little Enceladus would be spraying the contents of a hidden ocean into space. We went because the worlds were there and worth reaching, and again, what we found was stranger and richer than anything we had imagined before we left. That is the quiet argument for patience hidden inside every one of these long journeys. The reward for crossing all that distance is not the confirmation of what you already believed. It is the thing you never could have guessed, waiting at the end of the wait. That is the thing to hold on to. The travel times we have traced tonight are not really engineering footnotes, dull numbers in a mission report. They are a statement about where we stand in our own history, as a species that has only very, very recently discovered that there are other worlds at all. Step back and look at how fast that part has moved. A century ago, people genuinely did not know whether Mars even had a solid surface. 50 years ago, no human being had ever seen Jupiter up close. 30 years ago, we had never once photographed Neptune. And now, in the span of a few short generations, we have robotic emissaries in orbit around Mars and Saturn, machines that have touched asteroids and comets, a spacecraft on its way, this very moment, to an ocean moon of Jupiter. The pace of the individual trips is measured in decades. But the pace of the accumulation, the speed at which our reach and our knowledge have grown, has been astonishing. We are not stalled, we are simply early. It is worth letting the timescale of that progress sink in, because we are usually too impatient to notice it. The human beings alive right now are the first in the entire history of our species to know what the surface of another planet looks like. For every generation before ours, stretching back through all of human history, the planets were nothing but wandering points of light, mysterious and untouchable, the subject of myth and superstition and guesswork. And then, in the span of a single long lifetime, we went from not knowing whether Mars had ground to walk on, to landing machines on that ground, to driving rovers across it and listening to the wind. Someone born in the early part of the last century could have lived to see all of it, the entire transformation from total ignorance to intimate knowledge, compressed into the years of one human life. Measured against the age of our species, that is not slow. That is a sudden, almost violent awakening. The scientist Carl Sagan once said that somewhere, something incredible is waiting to be known. People often hear that as a poetic flourish, a pretty sentiment. But I do not think he meant it as poetry. I think he meant it as a prediction, and a specific one, about these exact bounded, reachable worlds we have spent tonight travelling among. Worlds with sunless oceans under their ice. Worlds with rivers of methane and skies of nitrogen haze. Worlds with chemistry and geology we genuinely do not yet understand. The question of whether life exists somewhere other than Earth, the question Sagan spent his life reaching toward, will not be settled by philosophy, or by argument, or by staring at the sky and wondering. It will be settled by a probe melting down through the ice of Europa, or a lander tasting the spray of an Enceladus plume, or a long, slow balloon drifting through the golden air of Titan. Those missions are, with the technology we have today, years or decades away. And that is not a reason to give up on them. That is the very definition of a long-term project worth having. There is one more way to hold all of this, and it gathers the whole night into a single feeling. Every travel time we have traced, days to the moon and months to Mars and years to the giants and decades to the edge, is really a measurement of how young our reach still is. We are a species that learned to leave its own planet only a single lifetime ago. The oldest people alive today were born before any object had ever been placed in orbit, before any machine had ever touched another world. And in that one lifetime, we have flung our small emissaries past every planet there is, landed on a moon of Saturn, measured an ocean beneath the ice of Europa, and stood, through the eyes of our machines, on the surface of a furnace and at the edge of the dark. The trips are long because we are early, and being early is not a failure. It is the most extraordinary place a species can possibly stand at the very beginning of its reaching, with everything still ahead. So here is what I would ask you to do. Tonight, or any clear night, go and find a point of light in the sky that does not twinkle. The stars flicker and shimmer, but a planet shines steady, a calm, unwavering point, and once you learn to tell the difference, you will never unsee it. When you find one, understand what you are actually looking at. You are looking at a world, a real place, a destination, somewhere it would take the best machine we know how to build months or years or decades to reach. Hold that thought for a moment without dismissing it, the way we so easily dismiss the things that are too large to hold. Everything we have ever launched, from the first small satellite to Voyager to New Horizons, left the bottom of this planet's gravity and crossed distances so wide that the sun's own light takes hours to span them, driven by nothing more than the belief that the trip would be worth making, long before anyone could prove that it was. And every single time, the trip was worth making. The solar system is not a backdrop, painted on the sky for our comfort. It is a neighborhood, and we have not yet finished exploring it. We are, if you take the long view, still very near the beginning of understanding where it is that we live.